As a final part of the course Ecological Modeling, you will use your programming skills to develop your own project. You will receive a template of an individual-based model and will adopt this according to the agreed projects. Projects can be feasibly developed in the next weeks and can range from disease, predator-prey to vegetation dynamics, and will include aspects of adaptive dynamics and pattern formation. As one of the most important parts of modeling includes its planning and reporting, I expect you to use the ODD protocol to describe your individual or agent-based model. ODD stands for Overview, Design Concepts and Details. You will use GitHub to share and discuss your code in the group. As a start, we will create what I shall call a simple bunny model. As individuals are at the basis of our models, we start creating them as a separate class. Every class has an initialization of the object in which attributes of the class, here the individuals, are defined. We here create an individual bunny of age 0 and an energy reserve equivalent of 10 carats. The function getOlder defines the aging procedure, with a self statement allowing you to bind traits like age to the object, here the individual. Every individual calling the function getOlder will thus increase its age with a factor 1. To get the individual alive and kicking, we create an instance of the individual type, here bunny, and print its traits. Besides just printing traits, we can now also create action and let the bunny age. You will see that the procedure bunny.getOlder gives exactly the same as manually increasing the age trait with 1. We can also pass information from the action to the function. As an illustration, we here create an eating function, in which individuals can increase their amount of resources with n carats. If we define the n carats as 5 in the individual action, you will see that the resources are augmented by 5 and will be 15 in total. Till now, our bunny experienced action at one moment, so as we defined it. By adding time loops, the code will then allow a sequence of here max time events in which the bunny's functions are called. Now we also implemented some basic respiration by burning the equivalent of 3 carats every time step of aging. We till now assumed actions to be fixed and invariable. In real life, however, many actions are probabilistic. Chances of finding food may, for instance, be inherently stochastic. We therefore program a new foraging function, called searchFood, in which between 5 and 10 carats are found within a probability of 30%. This is the first probabilistic interaction between the environment and the individual. If resources are depleted, bunnies die. We therefore use the if statement to check this. The break statement allows us to break the loop when the individual has starved. Now, very important, we do not aim to model a single bunny, but an entire rabbit population. We therefore create a list for the population, called bunnyPop, and add individuals, so an entire class, to the list. We here create a list, so a population of 10 individuals. The population is of course changing during the simulation, here because of dead events. We therefore create every time step a new list, called oldPop, to model these actions. At the end of all the events, we add all the surviving individuals back to the main list, and by doing so, all dead individuals are removed. So our population is updated according to the simple demography. While it is perfectly possible to proceed in this way in a single population and to add stochastic events that represent chances of finding resources, it is often more realistic and wanted to have space explicitly modeled, so to represent the variation in resources in the landscape and the movement of the individuals. As the model becomes more complex, we use docstrings to document the code for ourselves, but also others who want to understand what we are doing. Since individuals have to move, they receive 2 extra characteristics, or traits if you like, that represent their position, an X and y coordinate. We also create a new function to make the individuals moving, and to do this in the beginning by randomly choosing one of the neighboring cells or staying in the same cell. Hence, x and y coordinates are allowed to change randomly with one value at maximum. We of course now also need a class that regulates the population. We refer to this class now as metapopulation, where we define the start population size and, for the moment, resources equaling 10. So individuals are now moving in an unbound landscape, and we should be able to track all changes in their position and changes in the population size. The implemented nearest neighbor displacement is simple and may represent certain movements very well. We, however, would like to make this more realistic and now allow correlated movements according to a specific step length or speed. We implement such movement steps by defining initial movement angle, called self.angle, with the angle in radials, and define movement within a restricted spatial boundary of max x and max y. We make walks more or less correlated by defining a diversion of this angle every time step. Diversion of 0 will result in a perfectly correlated straight movement, one of pi in a pure random walk. Using simple trigonometry, we now choose the new locations based on the speed and the angle. We create a torus landscape by defining the positions as the rest fraction of its position relative to the maximum size of the landscape. As in old computer games like Pac-Man, for instance, individuals leaving the population on the right, having for instance a position of 11 in the landscape of max size 10, will pop up on the left at position 1. We also add reproduction now and allow individuals to reproduce from age 10 till age 15. The number of offspring depends on the amount of resources and the cost of producing an offspring. Resources are thus equally distributed over all the offspring. Importantly, we shuffle the list to avoid lucky lineages in the beginning of the list, always eating first, for instance. Otherwise, we get very strange priority effects in which the first listed individuals get all the advantages and the remainder nothing. Especially when studying selection on traits, such as shuffling avoids strange computational bias. We also want to make the environment spatially explicit. We here create a landscape of 40 by 40 cells, in which cells get a fixed amount of 70 resources. We use the NumPy function, as this is very fast and efficient. We first create a matrix of max x and max y rows and columns filled with zeros, and add the initial amount of resources to each cell. This is handy, as we do not have to define our matrix every time we want to change the landscape. If we want, for instance, the resource to be randomly distributed, we may simply replace the 70 initial resources by a random integer at choice. Now, the max x and max y are attributes of the metapopulation class and defined accordingly. Since individuals forage, the resources will change in the landscape, and foraging will be conditional to the resource availability. We therefore check the local quantity of resources. If higher than 0, the individual will consume 5 of those resources. Unless less than 5 resources are available, then the individual will take all there is left. We also allow resource regrowth of 2 units per time step, up to a carrying capacity of 100. We here use the numpy.clip function to constrain the resources between 0 and 100. Of course, we also need to track or to monitor the changes in the populations or the landscape. To track the distribution of the individuals, we define the array dispop, which summarizes the total number of individuals represented in each grid cell. Starting again from a null matrix, we increase the values of each cell with the number of offspring born and with the surviving adults. We can visualize our results in different ways. In the final model, we usually write all output in text files and make graphs and analysis at the end. However, we may also want to have more fancy visuals. We can make moves of dynamics, for instance, for presentations. We do this by using the ffmpeg package. This is no standard package and needs to be installed from the conda command line. If you don't succeed in doing so, then no worries. We can also use more static graphs using matplotlib. After importing the library, we define new lists for data of the graphs, here the x and the two y variables. We will plot the time on the x-axis and the population size, length, self-population as one variable, and the mean resource availability as a second y variable. We set our different graphs with upper figures representing the population size distribution, this pop array, and the upper right figure as the resource matrix. The lower graphs represent the XY figures defined earlier. We order the figures accordingly in subplots and define titles, and also create the animation of the entire figure as an MP4 movie. As mentioned earlier, maybe most important is to save all the raw data. We therefore have to create an output file, write our data to the file, and close all to save the data on your computer. Storing and exchanging your code is done professionally by using the GitHub platform. Now you're ready to start up your own group project.